Today we're going to be looking at the 2021 January Gold question, telephone. So in this question, Farmer John's and cows are standing in a line, and each cow has a breed identifier in the range of 1 to K. So the cows want to transmit a message from cow 1 to cow N. So the only rule in this question is that a cow of breed I may or may not be able to transfer a message from a cow of breed J. So if cow 1 is breed 2 and cow 2 is breed 4, they may not be able to transmit a message. So what we're given is the cows and their breeds, and then a matrix of which breeds are able to talk to each other. And we want to give the minimum amount of time needed to transfer the message. So the first algorithm that most people would think of doing this question would be Dijkstra's. And typically what you would do is you would implement a very basic, very textbook Dijkstra's, and what would happen is you would time out on 1 or 2 cases. So what's actually going to happen is if we were to use normal Dijkstra's, we can realize that the runtime is around O(n)². And in this case, that's not going to pass. So in order to optimize this, we're going to do one main thing. We're going to use edges. So the reason this is going to work is, let's say we're using a priority queue for our Dijkstra's. So we'd have, say, like while it's not empty, and then we'd visit it, give it its distance, and then we'd loop through its neighbors. So we can basically assume, worst case, we have our outer loop here is n, and then looping through its neighbors is another n. And so that is not going to pass. And what we're going to do instead is we're going to basically try and reduce the inner n loop. And in order to do that, we're going to find less edges. So what we're going to do is, instead of having from, let's say our starting node is 1, instead of starting from 1 and going to, say, n-1 other nodes, what we're actually going to do is we're only going to have 2 nodes as options. So only 2 edges. We're either going to go forward or go back for every k. So let's say we're starting at node 1. What we're actually going to do is we're going to create a scenario where we only have around 2k edges, so at most 100. What we're going to do is we're going to find every compatible type. So let's say type 3 is compatible, or breed 3 is compatible with this. And what we're going to do is we're going to find the closest one to our left, the closest one to our right, and we're just going to push those nodes in. We don't care about other nodes here or here. We only care about the 2 closest nodes with this breed type. And the reason this is going to work is, if we use logic, the most important thing you can note is, since the distance is linear, what we can note is, if I were to go and I were to start from A, and then I were to, let's say the optimal solution is to go from A, and then to this B, and then to this C. So what we can actually realize is, if I were to go from this A to this B to this C, it would be the exact same distance. So it would still be an optimal solution. So the reason why this is important is we can basically note that no matter which B we go to, since both B's can reach C, and we know both B's can reach C, we can basically realize that there's no difference. So instead of pushing, say, this one and we're going to push this one, we're just going to push the node closest to A with this breed type on the left and on the right. So we're going to push this value, and we're going to realize that they're still going to be the optimal solution. So what we can do with this is we're going to use a binary search. So if we were to, say, imagine out a pseudocode, it would look something like, I have my while loop for the priority queue, and then I do stuff here, I visited it, and then I'm going to find my neighbors. And in order to find my neighbors, I'm going to loop through the k different types or breed types, and then I'm going to do a binary search here. And then what we're going to do is we're going to find the closest one to the left, and then see if we can push that. And then we're going to find the closest one to the right and see if we can push that. And then once we find these 2, we're going to push them into the priority queue. And what we've effectively done is we've basically created a scenario where we don't have that many edges because for every value, I only need to go to the closest to k. But we've created a lot of nodes, and this is going to run a lot faster. So that's going to be the basic idea of the optimization. And the hardest part is realizing that these two are going to be exactly the same for the reason that if breed B can reach breed C, that means both of these points can reach breed C. And so there is no difference between A to B and B to C, and A to the second B and B to the C. So there is one special case we're going to have to note when doing this optimization, and that's just that if I were to have a scenario where A goes to the closest B, B goes to the closest C, and let's say our N is also this value C, or breed C. The problem here is that since B has gone to the closest C, what's actually going to happen is if C cannot go to itself, then we're going to return -1 instead. In this case, what we can actually do is we're basically going to check every time we pop a node from the priority queue, and we're just going to check whether or not this value is able to reach C. So if it is able to reach C, what we're actually going to do is, I'll show you more of this in the code, but we're going to basically calculate this distance plus the current distance of reaching B. So what that means is, just like in a typical Dijkstra, we're going to have a distance. So once we reach this node B, we're going to have this distance, and what we're going to do is we're basically going to check the distance of this, and then we're going to add the distance between it and N to get a possible answer. And then what we're going to do is we're going to continue on our program, and we're going to min the answer between that and other answers we get. So what I'm basically trying to say is the distance it takes to reach here plus the distance between this current location and N is going to be a plausible answer we're going to actually need to consider. So let's go move on to the code for this question. So I've set up the program a bit here. The main thing you need to know is I've typed def long is LL, so anytime you see LL, it means long. So the first thing we're going to do is we're just going to read in the input. And actually, even before that, we're going to set up our data structures. So I'm going to create my data structures, and I'm going to explain them as we go. And then we're going to resize them and read in the input. So all we're going to do is we're going to create two main things. When we read in the breed, we're going to create a cow breed list, which basically maps the cow to its breed, and also the cow breed lists list that's going to map the breed to the cows. So it's going to be two-dimensional. We're just going to have every breed have a list of cows. And then we're going to read in the matrix. So the next thing we're going to do is, since we're doing Dijkstra, we're going to be using a priority queue. So I'm going to enter in the first element, and that's just going to be node 1, and it's going to have a distance from 0. And then our distance array is going to be called distance from 1. And then we're going to do a typical Dijkstra, and before we get into searching for its neighbors, we're going to basically check two things. We're going to have if n is equal to n, so this just means we've reached the final cow. And the other thing we're going to do is we're going to do our special handling. So over here, we're going to check whether or not our current location is reachable to the last element. And if it is, then we're going to say we can actually consider this for the answer. Because what this would mean, just like we described earlier, is it's just going to be the current distance of n, and then we're going to add the distance between the last node and the current node, so big N and little n. And what we're going to do here is we're just going to realize that in typical Dijkstra, you could probably just return here, but because we have to consider that there are cases here, in particular for this exact question, test cases 6 and 10 or 11 are going to need this special handling, then we're going to simply create an answer, and we're going to use the minimum value rather than directly returning here. So all this is just to say we're going to do the special handling here. And the next thing we're going to do is we're going to look at its neighbors. So we're going to mark it as visited, and we're going to have a value called KK. So this is going to be looping through all of the breed types. We're going to check whether or not the breed type of our current cow, N, is compatible or reachable compared to this breed type, And then what we're going to do is, this is the optimization. Instead of doing a normal Dijkstra, in which we would literally just loop through every cow within this breed, what we're going to do is we're going to find the upper bound and the upper bound minus 1. So what this means is we're going to be using binary search, and we're going to use a binary search to find the number 1 greater and the number 1 smaller than our current value. And what this is going to do is it's basically going to find the closest two values, or the closest two cows to the current n node or cow. So what we're going to do is we're going to check boundaries. So if there is in fact a cow that is to the right of our current cow, we're going to insert it into our priority queue, and we'll write a function for that. And then we're going to do the same thing for the left. So there is a little bit of complications in the left. So what we're actually going to do is, in the case where the current cow is compatible with its own breed, which means I can find other cows in the same breed and I can transfer a message to them, what we're actually going to do is we need to make sure that we don't just push ourselves again and then we actually grab the node to the left. So in a typical case, we would just do the IT minus 1, or the upper bound / lower bound minus 1, because that would basically be the number to our left, or the cow to our left. But instead, what we're going to do is we're actually going to need to make sure that we find the cow that is not ourselves. So if it's the same breed, what would actually happen is IT minus 1 would be the cow itself, since we're using upper bound. But what we're going to do instead is we're going to make sure, and we're going to use IT minus 2 to grab the left cow. And then we're just going to insert the value here. So the insert function itself is pretty typical to a normal Dijkstra. We're going to check whether or not it's visited, and if it is visited, we're going to find its current distance, check whether or not it's less than its last distance, and then if it is, we're going to assign the value and push it into our priority queue. So over here, we're going to insert the left and insert the right, assuming that they're valid. And then at the very end, we're just going to output our answer. So in the case, if our answer hasn't been assigned a value, so if it's still the original long max here, then what we're going to do is we're going to output -1. Otherwise, we're just going to output our answer. At the very end, we're just going to return 0, and that's the end of our program.